Part 2. Okay, so let me get this up and running. So matter with part 2. Now we're going to look at the 4 states of matter. Before we looked at the different types of matter with homogeneous versus heterogeneous, and also physical changes, physical properties, as well as chemical properties and chemical changes. Okay, but now we're going to look at the 4 states of matter. Basically, we're going to focus on 3 of them, but there is a 4th one called plasma. But we have a solid up here, and a solid has a definite shape and a definite volume. Okay, so like your granulated sugar, your textbook, your desk, the chair you're in has a definite shape and has a definite volume. But sometimes they have irregular volumes or irregular shapes, and so you still have to find the volume of it. So in order to do that, you have to do displacements. Then we have a liquid over here. Now liquids have a definite volume. I can measure that in a graduated cylinder, and but it does have an indefinite shape, meaning it's going to take the shape of the container it's in. So I can pour liquid in various different containers and it takes different shapes, but I can still measure that exact volume. Now gases over here have indefinite shape and indefinite volume, meaning if I were to put gas in a cylinder and squeeze it, I can compress it, but then I can release it and it can expand as well. So gases have that ability. Think of your tires. In the wintertime, your tires can go flat a little bit. In the summertime, because it's hot out there, the gases will expand, and so your tires stay inflated a little bit better. If your tires in the wintertime look low, you start driving around, you stop after been driving maybe 30 minutes, maybe an hour on the road, look, and your tires look a little more inflated because the heat from the friction of the tire actually will make it expand in there. The last type of states of matter is called plasma, and plasma is made up of these particles that are in nature that have a charge. They're either positive or negatively charged. Lightning is an example of plasma. And most of the matter that's found in the universe, such as stars that are in the universe out there, they are made up of plasma as well. Okay? Now, there is this law that's out there, and as scientists, after working and looking at matter on Earth, matter, basically, they realized really you can't destroy it. Or, hey, I'm not a magician, and I can't create the matter. So what they realized, if I take a sheet of paper and I burn it, okay, that's undergoing a chemical change there. Basically, I'm left with ashes. And you see the smoke in the air. So basically what we've realized is matter just changes different forms, okay, from one to another if it undergoes a chemical change, okay? So we see that matter is neither created nor destroyed. That's the technical definition there. And so the second bullet down here just kind of puts it in layman's terms to help you out. It just means that I'm going to transfer the form of matter from one form to another. So if I burn the paper, I'm left with ashes and, of course, the soot in the air. And you can see the stuff in the air, it gets diffused out. Now, a phase change basically is it's a physical change. This is not a chemical change. Phase changes are physical changes. So I want you to think of that P for phase and P for physical changes. And it's where I'm actually going to take something and I can change it from a solid to a liquid to a gas, or I could skip the middle one with the liquid and go directly from a solid to a gas, and basically I'm changing it and I can put it back in different forms readily, okay, and shift it from one form to another. So the different phase changes that we have out there are 6, and the first one is actually melting, and melting's kind of easy. It's where you take a solid such as ice and then it will melt down, put it in a warmer environment, and it will melt to a liquid. Freezing is where you take an ice cube tray and then you fill it with water, you put it in the freezer component of your refrigerator, and it will actually change from a liquid to a solid. Okay? The next one is vaporization. That's like if I take the water, put it on the stove, turn it up to maybe medium high. Let's not boil it yet. Let's just heat it up. After a while, you look out and you can see steam forming above the container. You can see it rising. And so what you're doing is you're changing that liquid to a gas. You're changing the water to steam. Okay? Now, in the fall, here we have in the fall, let me go back. In the fall, what we have is a great time where we'll get fog, and we'll start to get condensation on the cars because the temperatures are dropping. You'll start to get that dew on your car. And so that dew that you see form on the car is called condensation. You can go to a window, breathe hot air over your hot breath onto the glass, and then it'll cloud up, and that is actually condensation. You get that also when the bathroom with the steam, you get condensation on the mirrors, and you have to cool it down and then it changes back. So that change in difference in the temperatures can change the gas to a liquid there. Okay, so that's what condensation, you're moving it from a gas to a liquid. Now, deposition is where we're taking a gas and we're bypassing the liquid stage and we're going directly to a solid. Now, an example of that would be dry ice. And how they form dry ice is they take carbon dioxide, what we breathe out, carbon dioxide, and they'll take that in a tank and they'll squeeze it into this container, and when they pressurize it, it forms a dry ice block. And they use dry ice in transporting medicines. You can buy dry ice from Harris Teeter, some of these grocery stores around here, and trying to keep things really cold. Okay? So that's how you form going from a gas to a solid, forming the dry ice blocks. It bypasses the liquid state and it goes directly from a gas to a solid. And then if you take that dry ice block out and you just let it sit in a warm environment, it goes directly from the solid to the gas. And they use the dry ice as special effects in a lot of movie theaters to get that fog look. Especially Halloween's coming up in a couple of weeks, you will see where they'll have that effect of the witch's kettle brewing and you get this fog appearance, and that's actually probably dry ice changing to a gas, and then it kind of creates this smoky, hazy appearance. Okay, now temperature and phase changes. So one thing that we've realized is as an object undergoes a phase change, if I'm going to go from a solid to a liquid, or if I undergo a liquid to a gas, during that time they realize that the temperature remains the same. And all that energy, instead of the temperature, all that energy that's used to increase in temperature is actually used to change that form from a solid to a liquid. But once it's changed that form, then that energy will start to cause the temperature to rise. Okay? So during a phase change, you can see right here, flat line right in here. These flat lines that you see, let me get my pen. These flat line areas right in here show that, and right here, this is energy down here. I'll put an E for energy. It's in the horizontal axis, and we'll put a T on the vertical axis right here. So as you're going across, you can see energy is always changing. You're always seeing a difference there. But once I reach to this point, temperature doesn't increase anymore. It goes flatline right here. And that means it's undergoing a phase change. And we'll go through these. So number 1 identifies the solid. Number 3 is your liquid. And number 5 is a gas. So solid, liquid, gas. Now, if you're going from a solid to a liquid, the phase change here would be melting. So let me write melt here. So you're melting at this state, okay? And I think on your chart you're going to need to fill it in. But if I'm going from the liquid down to the solid, and we'll put it down below, you're actually freezing down here. So let me write freeze down here. It's kind of hard to write, but bear with me. So you're freezing. You're going from the liquid to the solid. All right, now up here, here's another flat line right here. This is also a phase change. As you can see, as temperature goes up, at that point it kind of stays the same right there. So when you're going from a liquid to a gas, you are vaporizing. So I'm going to write vapor up here. It's kind of hard to write, so I'm going to kind of abbreviate or write it a little bit shorter. But when you go from a gas down to a liquid, and this is going in this direction, y'all see that? So when you're going in this direction on here, to go from a gas down to a liquid, you're actually condensing. So bear with me. I'm going to write condense here. All right, whew, got that one. So again, I'm going to write a S for solid. This is the liquid, and this is your gas. Okay? So that's the different parts of the phase change. Okay? Now another thing to remember, boiling point is when a liquid goes to a gas, that point at which liquid changes to a gas. And for water, boiling point would be 100 degrees Celsius. These are just some common fact information. And when I want to freeze water, and that means I'm changing a liquid to a solid to get these nice beautiful ice cubes here, the temperature for water freezing is actually 0 degrees Celsius. These are just some basic information. All right, so heat is basically when you are transferring thermal energy from one object to another, okay? And a key thing to remember, and I want you to specifically highlight this right here, this component right here. Typically, heat will flow from things that are hot to cold. Not cold to hot, hot to cold, okay? So if things are hot, it will transfer out to things that are cooler. Okay? So temperature and heat are not the same thing. Temperature is me measuring that thermal energy. Temperature is a measure. So let me get my pen here. It is a measurement. So using a thermometer is basically it. If the temperature goes up, then those particles move fast. If the temperature drops, then they kind of are not as active. Okay? Now, thermal energy is basically potential and kinetic energy of objects. And we learned from energy previously that potential energy means it's at rest, and kinetic energy is energy in motion. And so on that one, it is where the objects are moving rather rapidly or slowing down, okay? And a lot of this is determined on how much mass an object has and its actual temperature and also what phase it's in. So solids are a little more compact, and gases actually have the greatest amount of thermal energy. They have that ability to move in there. They're not locked in, okay? Specific heat, though, is the amount of heat needed to raise temperature from 1 gram of matter to 1 degree Celsius. So what do I mean by specific heat? Every object out there has its own unique temperature in which it will go up 1 degree Celsius. So amount of energy it needs in order to raise it. So like this little object right here, gold, doesn't need a lot of energy to make it go up 1 degree. Whereas water, 1 gram of water, it definitely will need a lot more energy in order to get it to go up 1 degree. Think about this, metals, you're heating it up, metals will heat up very fast, very rapidly, okay? Whereas water, watch pot never boils. If you put a pot of water on the stove, it takes a lot of time in order to heat it up. So basically, if you have a lower specific heat, it's faster to heat up and also a lot faster to cool down. So like if I took the metal and put it in water, you can pick it up right away. But if I take that water and kind of touch it, it takes a longer time to cool down. Okay? So here we have some specific heat problems that we have. The first one right here, a metal rod and a brick are both in the sun. Assuming that both have the same mass, which property of matter makes one hotter to touch? And remember what I said, each object has its own unique, and on here they have their own unique specific heat. Okay, I thought I had the pen going there. All right. They have its own unique specific heat that allows one to get a lot hotter than the other. Okay? And here's another one. We have the liquids in 2 beakers have the initial temperature of 50 degrees Celsius and are left to cool. So this one has a specific heat of 2,400 joules per kilogram degrees Celsius. So that's the unit for specific heat right there. So basically alcohol has a lower specific heat than water. What will happen to the liquids? So on here, the alcohol, because it has a lower specific heat, it will cool first on there. Okay? Because the specific heat on this one is lower, it's going to cool down much faster than the water because it has a higher specific heat. And think about water, it just takes a lot longer to cool down because the other choices said the water's going to cool first. Well, no, it's actually higher than the alcohol, so it's going to cool down a lot slower. Both will cool at the same rate? No, the number values are not the same. And both liquids will remain at 50 degrees Celsius. They will not. This one will lose the heat faster. So your best answer is A. Okay? All right, now there are different ways you can transfer thermal energy. And one way is by conduction. And conduction means that you're transferring the energy by touch. Okay, so you can see I'm holding a piece of metal to a flame. Ooh, after a while it gets hot. That's why a lot of times with stirring things, a spoon, if you leave the spoon in a hot pot and you go back to touch it, ooh, that spoon's going to be hot. So conduction is touching. Convection is when energy actually travels in a fluid movement, like a fan movement. You can see right here, water boiling in a pot is circulating. Or I take a radiator heat and the air will circulate in here. Or using fans to circulate air. That's convection. So it's when the particles of a fluid move from one place to another. They're circulating. So in this one, you might want to say circulation. And the previous one before, you might want a hint word here is touching. Okay? So again, let me circle this one. So on convection, you're circulating. Okay? And this one's seen in just liquids and gases, whereas conduction is seen in all three, solid, liquid, and gas. And the last one is radiation. And radiation is when you're traveling, you're getting energy from the sun through space. And think of this one, the sun would be a great example of radiation. It's traveling in waves through space, and the sun generates that energy and gets us and heats us up. Okay? And here's a chart just to, again, give you the definitions as well as examples down for each of these. Okay? Okay, now the last thing that I have right here are conductors versus insulators. Conductors are basically those materials that allow heat to travel through. They allow thermal energy, and think of heat, to travel through, and the best ones are metals. And insulators, think about a cooler, they're an insulator. Your house has insulation in it. These materials do not allow, they're going to trap the heat in, or they're going to prevent the heat from coming in. So on there, examples, air and non-metal material, plastics, wood, things like that are all good materials that are insulators. Okay? All right. I hope this helps, and if you have any questions,